Okay. So this week we are going to learn something different. Okay. So past 2 weeks we have dived into understanding the CAD modeling part. Okay, and we also understood why it is important for 3D bioprinting, or let's say for additive manufacturing, for instance, like not just for 3D bioprinting, but if any additive manufacturing that you want to do, let's say using light or using normal 3D printing, using PLA filaments and all, the first step that one needs to learn is CAD modeling. Okay, so we have looked at it briefly and we had practice session as well. This week we are going to learn something different. We are going to start with the first topic of the course, that is extrusion-based 3D bioprinting. So briefly, I'm a PhD scholar at Chemical Engineering Department at IIT Kanpur, and every Sunday we meet at 6:30. Okay, this is the meeting link that we use. And in order to communicate, please use your mic to speak up. The chat option is not available. All right. So extrusion-based 3D bioprinting, that is the topic that we are going to discuss today in this week. Next week, we are going to discuss one paper that shows the application of this technique for printing skin tissue. Okay, so next week will be the application. This week will be the basic introduction on this technique. So what is this technique basically does? There is a bioink, all right? We have already seen what is bioink. So bioink is nothing but a mixture of cells or biological active components like growth factors or drugs or anything with a base biomaterial. So this base biomaterial is usually a polymer, okay? And we mix it homogeneously to create something called bioink. So that is the material that is extruded. And what is the process of extrusion? Extrusion means you are pushing some material like this bioink material out through a tiny diameter nozzle or needle. Okay, because of which you get filament like deposition on the platform, on the substrate. All right, that is the act of extrusion. So in daily life, if you use a syringe, okay, and load it with something like clay or anything like that, and then push it really hard manually, and you will see that the clay is now depositing on the surface like a thread. So that's the process of extrusion. Even when you make jalebi, right? So the batter is like the person making jalebi, he presses the um, pipe holding the batter, right? And it falls like thread over the oils. That is also a process of extrusion. Okay. Similarly, when you pipe cream over cake, all right. So that is also a process of extrusion. So that is like extrusion is a daily life process that happens everywhere. All right. So the similar act is used, this mechanical process is used for bioprinting as well. And the material here is a bioink containing cells and other biologically active component. Okay, so this bioink is loaded into a print head. Now, this print head in a bioprinter is often controlled by codes and all G code, like we discussed last week. Okay, the G code will dictate the movement of the print head. Okay, in XYZ direction, and as it is moving, simultaneously the bioink is extruded in form of filaments, and we get a 3D structure, like layer by layer, we get a 3D structure. Okay, that is the process of extrusion. So you can do extrusion in a machine in different ways. You can use pneumatic force like air pressure in order to extrude out your bioink. Like people use normal compressed air or nitrogen gas. So, and nitrogen is inert, so it will not react with the bioink. Similarly, air is used in compressed form. So this is the example of how this looks like. So so pneumatic air pressure is applied on the bioink from the top, okay, and the from the other end there is a needle or nozzle through which the bioink is extruded in form of filaments. Okay. Then mechanically also you can push the bioink. So people use piston or screw. Okay. So both of these piston and screw, they are directly in contact with the bioink. In pneumatic, there is no mechanical counterpart that gets in touch with the bioink, right? So this pneumatic system can be used for relatively low viscous bioinks, whereas if the viscosity is very high, then you use mechanical systems like a piston or a screw. Okay, screw basically it moves in a rotating manner. It rotates, okay, and pushes the bioink through the nozzle. In piston, there is just a single downward motion, that's it. Okay, so these three methods of extrusion are generally used in a bioprinter system. So how a bioprinter, extrusion-based bioprinter looks like. So this is an image of the bioprinter that we have in our lab. Okay. So we have print heads. So these are the three print heads. Okay. These are the three print heads. And this system uses pneumatic mode of extrusion, means it is connected to a air compressor. So pressurized air flows through the pipes. These are the inlets for the pressurized air to get in touch with the bioink. So this is a cartridge. This entire thing is a cartridge, you see. And at the bottom of the cartridge, there's a nozzle attached. So this is the assembled form of the system. Okay. From the top, compressed air comes, and within this cartridge, we load bioink. And as we apply some amount of pressure, extrusion pressure, from the tip of the nozzle, the material comes out. Okay. And this is the print bed onto which we can place a glass slide or a well plate or petri dish, onto which the material will get deposited. Okay. So this is the real image of a bioprinter, extrusion-based 3D bioprinter. Okay. Any questions in understanding how the extrusion-based 3D bioprinting works? Like the basic thing of why this technique is called extrusion-based 3D bioprinting. Any queries at this point?
Ma'am, basically it means using pressure we push the cells outside.
Yes, we
Okay,
push
ma'am.
bioink. You push bioink outside, yes, through a nozzle or needle. Yeah.
Okay, we are putting a pressure, right? But for a cell, there is a huge pressure, right? Uh, in billion cells, at least one or two cells may get broken or death, right? It will not cause any problem in while a tissue is developing. A single death
So
cell, like
yes, yes. So that is a very good question, and that is one of the limitation of this technique that will come and discuss in like future slides. Okay, in
okay,
next slides we will discuss this limitation. Okay, so let's talk first about the bioinks and how should you design a bioink. Like Murli said, the cells are vulnerable to high pressure. They are so tiny and the cell membrane are so weak. If we apply very high amount of pressure, it will burst, right? It will, so if you load around say 1 million of cells, there's a high chance that 80 90% of the cells will die. So how to protect those cells so that final outcome that you get, the 3D object that you get, have high cell viability, means higher number of live cells in it, so that you can mature it. So then comes the role of designing the bioink. What components would you put in it so that it shields the cells from this high pressure? Apart from that, also there are few factors involved. Okay, so we'll discuss here the design of the bioinks, of what things you should keep in mind. Okay, while designing it, what all technologies available currently based on designing bioinks. That also we will discuss. So bioinks, as I said, is a formulation of cells and other bioactive components, okay, mixed with the biomaterial. So this biomaterial is usually a polymer, although people are trying out different classes of biomaterials as well, but main biomaterial that is used is a polymer. And if you categorize polymers, there are different type of polymers like thermoplastics are there, hydrogels are there. So mainly the hydrogels are used as in the Bioink formulation, because hydrogels, they can retain a large amount of water, okay, maybe double its weight or maybe triple its weight, okay. So because of that, the cells can thrive well in an aqueous environment if you use hydrogel. So we want to, since the ultimate goal of this 3D bioprinting is to fulfill the objective of uh, mimicking the in vivo tissue environment, right? So in order to do that, we use hydrogels to provide cells with an aqueous environment that is already there in our body. So if anyone asks what type of biomaterials are used for making bioinks, these are actually hydrogel polymers. Okay. So these two are mixed together and they are deposited using an automated robotic arm that we talked about, like the G code and all, how the G code instructs the movement of the printhead in XYZ direction. So it is, the deposition is highly automated. So what properties the Bioink should have? First, it should have good printability. So when you first start working in this area, you will see that in your initial trials, the formulation that you're making may not be printable. Means it will, whatever desired shape that you have in mind, that shape will not retain. We I commonly face those problems a lot. So it will start spreading on the substrate, right? Or it will be too viscous for to be extruded out. So ultimate outcome that you are looking for may not be the same that you gave in the, like, as a CAD model. Okay. So that is called printability. Printability means whatever you have desired to print, whether or not you're able to print that. So in very simple words, printability is the ability to get printed into a desired shape. Okay. That is the first and foremost property that a bioink should have, that it should print the desired object, or it should match the CAD model that you provided. Okay. Then the printed structure, it should have good fidelity with the original CAD model. Okay. So the shape that you got after printing, it should hold it shape. Okay. Even after printing, like sometimes due to weight, the heighted structure starts collapsing. So those things should not happen. It should match the original CAD model in height, length, breadth, everything. So that is one objective of printability. So if you try to um, define the term printability, it's a very big term. And under it, there are umbrellas, small umbrellas are there, like fidelity, shape fidelity, it is called. That also comes. Then under printability, we also check whether the material can be extruded. That is called extrudability. So there are some materials that does not get extruded because it is too viscous. Or even if it gets extruded, it extrudes like water. Okay. So we want extrusion of correct type so that you get smooth filaments every time. Okay. So that is one aspect. Then how much the filament that you're getting after extrusion, how does it look like? Is it uniform enough? Is it thick enough? Is it matching the diameter of the nozzle? So we test that as well. So we classify the filament properties as well. So there are various small like properties under printability that we check to assess how good our bioink is. Then once these two properties match, like, okay, fine, you have made a bioink that has a very good printability and it can give you the original shape of the CAD model every time. Okay, then how good is your bioink in shielding the cells from the detrimental effects of the shear stress? Okay, whether or not within your bioink the cells are alive, how, what is the percentage of cell viability that you are observing after bioprinting? Okay, that is third aspect that one should look at. Okay, so when we talk about shear stress, how the shear stress is happening, so when the pressure is applied from the top, okay, so the cells are basically that are most near to the walls of the cartridge, they will basically face a shear force. Okay, they will rub against the wall of inner wall of the cartridge. That is why the cell will lyse. Directly, the pressure will not kill. Like even the piston, if the piston is there, hardly few cells are in contact with the pistons in the 3D surface. Most of the cells may be near the walls of the cartridge. So because of that, they will face some shear forces and they will die. So how good is our Bioink in like shielding that effect of shear stress? Also, we often use various levels of chemicals like um, to cross-link, or we can use light, then we can vary the temperature and all. So all these things that changes in the environment, that can also, those environmental effects can also have a detrimental effect on the cells. So why we do it? Why we change the temperature, light, and then pH and all in order to maintain printability. Okay. So we there is a compromise. Like if you maintain good printability, then you will have to face some loss in cell viability as well. But if you want high cell viability, then the printability will be compromised. So we have to think of novel ways in order to increase the printability, okay, while retaining very high cell viability. So these two trade-offs has to be balanced, and we the final objective of every researcher in this area is to get very good printability with high cell viability. Okay, so these are the three properties that a bioink should have. Any questions? All right, if there is any questions at anywhere, yeah,
You
go
said
ahead.
most cells will be in the walls of the nozzle, right?
Towards
How?
yeah.
Why, ma'am? Because of its weight
So
compared to
like
other.
so it's 3D. So the hydrogel is usually this, we load a solution form of a hydrogel. Okay. So that it is easy to load. If it is already gelled, then it will be very difficult to load in the cartridge. So when it is in solution form, the cells are homogeneously mixed. So like many cells will be near the wall, many cells will be the inside. Okay, so it's like you cannot see the cells exactly like in the cartridge, but any cells which are near the wall, they will face the highest shear stress level. That's what I was talking about.
Okay, okay.
Okay, but the cells which are inside, like in the core, you don't know, right? How many cells are there in the core and how many there in the wall. So core cells, they will be relatively experiencing less shear stress.
Okay, ma'am.
Okay. But you cannot control it. You cannot control how many cells are there near the wall or near the core. You cannot control it. Okay.
Hmm.
Yeah. Um, Next point that we are discussing is that Bioinks, water bioinks. So they are usually non-flowing gels. So they don't flow on its own like water. If you pour some on the table, it will flow, right? Very easily. But bioinks, they're usually non-flowing with sufficient viscosity. It should have some level of viscous nature in it. And it will only begin to flow when its yield stress is exceeded. So yield stress is defined as the stress, minimum amount of stress that one needs to apply for it to flow, for this bioink to flow. Okay, that is yield stress. So how we are exceeding this yield stress? When we apply pressure. When we apply pressure, this yield stress of the bioink is exceeded, and then only it will start to flow. Otherwise, it will stay inside the cartridge as it is. So the transition from this non-flowing gel to a fluid like low viscous state. Okay, so this transition happens. So the inside initially it is non-flowing gel. You apply some pressure, the yield stress is exceeded, and it starts flowing. Its viscosity decreases. Okay, it this is a property of a shear thinning fluid. Okay, so what is shear thinning? Shear thinning means those viscoelastic fluids. Please listen carefully. Shear thinning means those viscoelastic fluids whose viscosity decreases when shear increases in it. And as soon as the shear force is removed, its viscosity again increases. Again, let me um, quickly describe. Shear thinning fluids are those fluids whose viscosity is decreasing when the shear forces are applied. And as soon as you remove this shear force, its viscosity decreases. So these kind of shear thinning fluids are usually used as bioinks for this technique. Okay, so these bioinks have a threshold value of yield stress that needs to be exceeded. When you exceed that, it will transition to a low viscous flowing character, like flowing property, like it will start to flow. Okay, and it will then get deposited on the surface. And on the surface, there is no more shear forces acting. So its viscosity again increases and the structure is retained. So molecular level, what is happening? Due to shearing, some bonds, some molecular bonds, they get broken. Okay, they dissociate from each other. Because of it, the viscosity, overall viscosity decreases and it starts to flow. But as soon as you remove the shear force, the bonds again get formed and the viscosity increases. So it regains its shape. Got it? So when you are using shear thinning fluids, you can actually ensure that the cell viability is good. Why? Because upon applying of shear force into this fluid, overall shear inside the fluid, what is happening? So the overall viscosity inside this fluid is decreasing. So in less viscous environment, the cells can move around. So even if the cells that are more prone to death due to their presence in the wall, so they can actually move now in the low viscous environment. Okay, and safely can come out from the nozzle. But when the shear forces are removed, the cells that are deposited along on the surface, they will now like expand in a high viscous environment. So the position of the cells in the high viscous hydrogel, they are now fixed. If you use if you don't use shear thinning fluids, then there is no chance for the cells to move around because the viscosity is very high. It will be not able to penetrate throughout the hydrogel network, right? So the cell death will be higher. Got it?
Yes, ma'am.
Any? Hmm. Also, shear thinning fluids also allows the use of low extrusion pressures as well, relatively, if you don't use a shear thinning fluid. So there is another kind of fluid that is called shear thickening. that is like complete opposite. Okay, so uh, shear thinning fluids uh, are the main type of fluids that are used for making bioink. Why? Again, let me repeat why. Because the overall viscosity of the fluid gets reduced on application of a pressure. Okay, they also have relatively less value of yield stress, because of which you will use less value of extrusion pressures. As soon as you apply this extrusion pressure, the overall viscosity decreases. Cells are very happy in less viscous environment, so they easily get extruded out. But as soon as you remove this shear force, means on the platform there is no shear force, the viscosity increases again, and the cells are now very well placed in the 3D space in the high viscous environment. Okay.
So,
Any
ma'am, this
queries?
shear
Yeah.
force is applied by piston, or it is any other medium?
So I told you here. So you can use a piston to apply shear force. You can use a screw, or you can use simple air pressure in order to push out or in order to extrude the bioink. So when you are applying some external pressure, shear forces inside the fluid are generated.
Understood, ma'am.
Okay. Hmm. So after, as I told you, after the bioink is extruded on the bill plate, it will regain its high viscous state. Okay. Molecular level, at the molecular level, whatever bonds that were dissociated due to the applied pressure, they will start to reform again. And which is why the shape that you provided as a CAD model, it will be like that. It will not change over time. Okay. Now, often some bioink require a post printing processing. Like after you print, you do some processing on it in order to make sure the shape that you gave it it should retain. Okay. So people use some chemicals, okay, to form permanent bonds, or use some physical methods as well. So if you don't do it, what happens is these bioinks will simply dissolve away. The structure that you gave, it will simply dissolve away in cell culture media. Okay. So that is why, to retain that shape that you gave, some uh, after printing cross-linking methods are used. And they are done before you start the culturing process, cell culture process. Okay. So how do, like, what technology are available now for designing these bioinks? What type of materials should you think about when you start your bioprinting process, like the journey? What kind of materials are available? And I'll show you some examples of these materials. And all these materials that I'll discuss, they are already being used in the literature for this extrusion-based 3D bioprinting. The first design concept that I'll discuss is you use only one bioink, but this bioink can be chemically cross-linked. So when we talk about chemical cross-linking, it means we're talking about formation of covalent bonds among the polymer chains. Physical cross-linking is like reversible in nature. The physical forces like electrostatic forces or ionic cross-linking or like entanglement between the polymer chains, they are all reversible. But chemical cross-linking, they are permanent. Okay. So people use in this, under this method, people have used various type of methacrylate modified polymers. So what is this methacrylate? Methacrylate is a group that allows polymerization, free radical polymerization, and formation of covalent bonds among the polymer chain in presence of light. So this methacrylate group has been added to the backbone chain of various polymers, and some polymers that came out as a result of it, they are now called as gelatin methacrylate, gelatin methacrylyl, or gelma. Okay, gelatin is a very well used polymer, biopolymer used, and at the backbone, this methacrylate group is added. Okay, then PEGDA or polyethylene glycol diacrylate. Okay, so here also PEG is another very well-known biopolymer, PEG or polyethylene glycol. At the backbone of it, diacrylate group is added. So because of the addition of this methacrylate group, these polymers can now be covalently cross-linked by the mechanism of free radical polymerization in presence of light. You can either use UV light or visible light, and there is some photoinitiator also that is added to initiate this free radical polymerization process. What is free radical polymerization, you may ask? So here what happens in presence of light, first this photoinitiator is activated and it releases a free radical. Like you must have seen groups like this dot. It is highly reactive and it will now target the next bond. So this free radical is generated. Now this free radical can target the methacrylate group. Okay, and some like that again generates another free radical on it. So in this way it's like a series thing, it keeps on happening and happening. Okay, so there is an initiation step, there is a progression step, and it will terminate. So it's a like a chain process, like one free radical starts targeting another free radical starts targeting another. In that way covalent bonds are formed. But here the key point to be noted is that people use visible light or UV light, means a light source, and a photoinitiator to start this free radical polymerization and form covalent bonds in these polymers like GELMA or PEGTA. Okay, this is one way, one type of polymers that are used. There are other polymers also which are functionalized with other groups, like not methacrylate, but other groups like norborine or allyl. And these groups allow another type of uh, chemical reaction that is called thiolene reaction. Now here mechanism is slightly different from the free radical polymerization. Here what happens, the polymers, they are functionalized with norborine or allyl groups. These groups have carbon-carbon double bond. Okay, they have carbon-carbon double bond. And these carbon-carbon double bond, they are attacked by thiol-bearing crosslinkers. Thiol means SH group. This SH group goes and targets this carbon-carbon double bond and then forms covalent bonds with it. Okay. So again, this process happens in presence of light and a photoinitiator. If these two things are there, so again the photoinitiator will go and attack these thiol bearing crosslinkers, and this thiol bearing crosslinkers will go and attack the carbon carbon double bond that is there in this norborine and allyl groups. Okay, and thus uh, covalently crosslink the polymer chains with each other and create a permanent type of um, network, hydrogen network. So so this is, this figure shows the mechanism of how a polymer gelma is cross-linked. So you can see this group is basically methacrylate group that are hanging out from the backbone chain of gelatin in presence of a photoinitiator that is called Agracure 2959, and in presence of UV light, what happens? These methacrylate groups, they now react with each other. These two are getting reacted and forms covalent bonds. Okay, and thus forms the network, hydrogen network that is more stable. The next example where there is thiolene reaction happening, here there are groups that is called norborine groups. Okay, that are again hanging out from the backbone in presence of UV light. Again, LAP is a type of photoinitiator, and in presence of DTT, this DTT group contains the thiol group. Okay, so uh, in presence of all these three things, these norborine groups, you will see These norborane groups contains carbon-carbon double bond. They are attacked by the thiol group of DTT, and the DTT is now helping to form crosslinks, bonds like bridges among the norborane group. And as it does it, the polymer chains are now covalently cross-linked. Okay. So here only one type of bioink is used, and the structure, the final structure of the 3D print that is made using this bioink is stabilized by chemically cross-linking it in presence of light and a photoinitiator. But there is a limitation. These polymers that are used here to make the bioink, they often show printability issues. The initial state of that bioink is very much like water. It flows very easily. It does not have very high, like it does not have sufficient viscosity to start with. So we often, how we circumvent this issue, we often mix this modified polymers with other polymers which can give some sufficient viscosity, and in that way we can like overcome this issue. But it gives this polymers gives a very fast, smooth, okay, uh, technique to photo crosslink or chemically stabilize the structure. You can just shine light after the printing is done. You don't have to take the structure out or distort it in some way. Like on the build platform like on the surface of the build platform, you can just shine light and your structure is good enough for the next step. Or what you can do, you can shine light during the process as well. And as the filament is extruded, okay, it is cross-linked and getting deposited. So like it offers various uh, ease to the researchers to work with. That's why these polymers are becoming very popular in the area of 3D bioprinting. Okay. Now, the second type of bioinks that are used is these bioinks can be chemically cross-linked, but in presence of enzymes. In the first examples, we saw that it can be chemically cross-linked in presence of light, right? Here, in presence of enzymes, you can chemically cross-link. So there are the backbone of the polymers, they are modified with some amino acids like glutamine or lysine. Okay. And these glutamine or lysine containing groups, they react with enzymes like transglutaminase or horseradish peroxidase. Okay, these enzymes can act on these groups, because of which you get a cross-linked structure. Okay, so it's very easy. Here, you have to just mix your bioink with an additional component like transglutaminase or horseradish peroxidase. You have to mix with it and allow some time for the enzymatic reaction to happen to give you the final chemically cross-linked structure. Okay. Any queries here in these two bioink designs?
No, ma'am.
Okay. Okay. Moving on. Now you can also make multi-component bioinks, like you mix 2, 3 types of polymers with each other and make a bioink. So this is a very common approach when you're using, let's say, Gelma or Pegda, which I told you inherently they are not very viscous in nature. So you can mix with polysaccharides, mix them with polysaccharides like alginate, sodium alginate, or carrageen. So these are basically derived from plants, like alginate is derived from algae, carrageen is also derived from algae. The beauty of these materials are that they are viscous in nature. Okay, it doesn't flow very easily. So you can mix these materials with Gelma or Pegda. So then you can take advantage of two type of cross-linking mechanisms. Alginate or carrageen, they will get cross-linked in presence of ions, usually divalent ions like calcium or barium ions. So this shows a mechanism called ionic cross-linking, but this is physical in nature. So if you use a chelating agent like EDTA to remove those ions, then the cross-linked structure will be distorted. Okay, but it's good. Like you can first do the ionic cross-linking, and then to make the structure more permanent, you can use chemical cross-linking, okay, in presence of light, if you have mixed with Gelma. Okay, so that again gives you a more stable structure, and it will make your bioink printable. Okay, so here in this figure, it is showing there's two polymers, like say polymer A is your Gelma, this polymer B, let's say it's alginate, okay? And alginate, so when you mix alginate with Gelma, you have sufficient viscosity, you print it on the surface, then you use some bath containing, salt bath containing say calcium ions, okay? You dip the structure in those calcium ion containing bath, so ionic crosslinks are formed. So their structure is somewhat stable now. Then you do a second cross-linking step where you use UV light or visible light to finally form the covalent bonds and make the structure much more permanent. Okay. Then this is the fourth type of Bioink designs that is very well reported in the literature. Here we use physical cross-linking method to stabilize the final bioprinted structure. Okay, so what is this type of physical cross-linking is called supramolecular guest host interaction. Okay, guest host interaction, but it is physical in nature, means you can distort this interaction afterwards. So this image that I have taken is from a paper by Jason Burdog's group. So they have developed this two component system. The base material that they have used is hyaluronic acid. One batch of hyaluronic acid is modified with a molecule that is called adamantane. Okay. And another batch of hyaluronic acid is modified with molecule called cyclodextrin. So cyclodextrin, you can see it has a structure like a cup. Okay. Like a funnel. That is open on both ends. Okay, that is structure. That is a like very simple representation of the structure of cyclodextrin. Whereas adamantane, it has a structure like a ball. So this is adamantane here. So when these two batches or when these two types of modified hyaluronic acid they are mixed, then adamantane goes and sits within the funnel of cyclodextrin. So you see, cyclodextrin is providing it um, place, a configuration for the adamantane molecule to sit inside. So cyclodextrin is what? Your host, and your guest molecule is adamantane. So this is called guest host interaction. And since this interaction is based on the configuration of the molecules, so that comes under supramolecular chemistry. Okay. So that is why it is named as supramolecular guest host interaction. And it is physical in nature. Let me remind, it is physical bonding. You can always use some other inhibiting forces to remove the interaction between adamantane and cyclodextrin molecule. Okay, so this type of physical interaction allows very good printability. Why? Think in this manner. When you have mixed these two components within your cartridge, it is like showing this interaction, right? The molecules are very well placed, like guest host interaction is in place within the cartridge. When you apply shear forces, like by applying some extrusion pressure, these molecules, as I said, they are physical, so they will start dissociating and the material becomes much more flowable. Its viscosity, overall viscosity decreases. So because of which it extrudes out very nicely from the tip of the nozzle. It extrudes very nicely. And as soon as it gets deposited on the surface, then what happens? The gaseous interaction again starts forming. So, and their structure becomes stable. So this type of physical interactions or this type of physical cross-linking actually helps in achieving good printability for your bioink. Okay. Then if you want to make this structure much more permanent, then what you will do? You will add some chemical groups like say norborine or allyl groups, or you can add methacrylate groups so that you can chemically cross-link them, the final structure in presence of light. Okay, so there is bit of polymer chemistry involved, but it makes the overall design of the bioink very easy to handle and work with. Okay, any questions? Everyone understood how the guest host interaction works?
Yes.
Okay. Then another type of bioink design involves the use of nanoparticles. Okay. So you understand what are nanoparticles? These are very small particles whose size is in the range of nanometers or in the range of submicrons. Okay. So if you mix these polymers, some polymers with nanoparticles, these nanoparticles can help in increasing the shear thinning property or enhancing the shear thinning property, as well as it can act to mechanically strengthen the biomaterial, and it can also act as a carrier for drugs or say growth factors, etc., to get encapsulated or conjugated with these nanoparticles. Okay. One example is of laponite mixed with cellulose. So laponite is a type of nanoparticle. It has shape like this, like disc, but the sizes of each disc is in the range of nanometers. Okay, this is the structure of laponite, very simple representation. Whereas cellulose is a type of a cellulose called carboxymethyl cellulose. It is a very high viscous polymer. Okay, and it has some like electrostatic charge associated with it. Laponite is also like having some electrostatic charge. So when these two polymers are mixed and some cells are also added, then what happens? You will see these two components, they get mixed with each other very nicely. Laponite contributes to enhancing the shear thinning property of the biomaterials of the bioink, and also it can act to conjugate with some growth factors and anything like that. And laponite itself is not toxic to the cells. So if you use very less percentage, like 1% or less than that, the cells will grow very nicely around it. Okay. So you can use nanoparticles as well to enhance your bioink composition. Okay. Then you can use bioinks with sacrificial materials. Okay. So as I told you, the printability of a bioink is very important. All right. And in order to increase the printability, common sense says that you need to increase the viscosity of the bioink. But in order to do that, what you can do, you can either increase the concentration of the polymer that you are working with, or you can use multiple components in it, right? In order to increase the overall viscosity. But if you use a very high polymer content, then the cell viability is often reduced. It is shown, okay? If the polymer to cell is very high, the ratio is very high, the cells will have less space inside the 3D environment to move and grow and proliferate. So the overall cell viability in long-term studies will get reduced. So in order to improve that, we can use sacrificial materials. So the role of sacrificial material will be temporary. So you use those materials initially in order to increase the viscosity, but after the printing is over, you remove it. Okay, you remove it, let's say by washing step or something like that. You just remove the additional materials that are there. So what happens overall? You will be able to generate some empty space, void space inside the matrix, hydrogel matrix, that will give much more surface area for the cells to grow and migrate. Okay, so this is one example where gelma, as I told you, has very less viscous nature. It is mixed with PEO. Okay, it is again a polymer, but it's it is not like it is not cytotoxic, but it does not have any um, bioactive properties, PEO. Okay, but it is viscous in nature. So you mix PEO with gelma for printing. Okay, after printing is done, you use water. It dissolves very nicely in water. So you, after printing, you immerse in water. The PO will be dissolved out, and obviously you do it before the immersion of the immersion of the final structure will be done after you photo cross link it. So gelma will form permanent covalent bonds with PEO material embedded inside the matrix, and then you immerse in water, okay, for a few minutes. The PO will dissolve out, and once it happens, pores will start forming, will form inside the matrix, and that will give better space for the cells to move around. Okay, make sense why one should use sacrificial materials?
Yes, ma'am.
Right. Then you can also use microgels, only microgels as bioink. Okay, so what are microgels? You can first make a gel, like use gelatin, for example. You add chemical cross-linking agent like butyraldehyde in very low concentration. After some time, if you keep it in low temperature, you will see that gel is formed. Okay, you can hold it and squeeze it, like thick gel is formed, and then you grind it with some blender or something like that. Once you do that, the gels will crumble up into tiny pieces, and you will get a mushied up structure, very, and but it is flowable. That thing will be flowable, but the gel is already formed. Here the unit structure is the gel, hydrogel. In the previous examples we saw the unit structure is the polymer or the monomer, all right, but here the unit structure is the gel itself. And these gels, they can be mixed with cells, okay, and loaded into the cartridge. So the advantage of using this type of bioink is that these gels, these are just tiny size, right? Micro gels means very tiny size. So they can very easily squeeze in presence of shear force. Okay, so it makes the overall composition of the bioink highly shear thinning in nature. It can squeeze under presence of shear force. It will get extruded out from the needle very nicely and get deposited on the surface. So there, since they're already gel state, so it will confer better mechanical strength to the overall structure as well. Another advantage is that these gels, when they are packed, very well packed, tiny pores, inherent tiny pores will be there. So it increases the overall surface area for the cells to move around inside these pores as well. Okay, so this is another way of making bioink using hydrogels itself in microgel form instead of using any macromer precursor or something like that, polymer precursor. You're not using the polymer itself, you're using the gelled form of the polymer. All right. And lastly, you can use decellularized ECMs as bioinks as well. What are decellularized ECMs? So if you use a native tissue like from pig skin, let's say you use a pig skin and you use several methods like chemical and physical methods to remove all the cells very nicely, then you will get only the ECM. That is the decellularized ECM. Then why it is used? Because it has all the cell adhesion motifs and very good bioactivity. Okay, it promotes cell adhesion and everything very nicely in comparison to, let's say, gelatin or something like that. Okay, so that is why decellularized ECM or DECM is becoming very well popular. And if you make a powder out of it or you make a solution out of it, it gives sufficiently high viscosity as well. So yeah, it is viscous in nature as well. And you can also modify it by adding methacrylate groups or norborane groups in order to chemically modify it, in order to allow chemical cross-linking after printing as well. Okay. So main reason for using decellularized ECM is to make the bioink very well suitable for cell growth. That's it. Okay. Further modification for printability can be done on it as well by adding chemical groups and then other things. Okay. So any questions so far on all the 8 types of bioink designs that we discussed?
Ma'am, these all are standard ones, right? But uh, for everybody, the way they need to have a they will have an idea, right? For this type of tissue, I need to use this type of cells. For so in those times, they will come up with their own bioink, or even if they come up with, they only use these kind of techniques.
So there is 8 types. They are the most widely used. Okay. So definitely you're correct. Depending on what type of tissue that you want to bioprint and also the resources that you have. Let's say you have access to decellularized ECM because it is ethically very difficult to get, right? And also commercially, if it is available, it will be very expensive. So first you have to check what type of tissue that you want to bioprint, what type of cells that you're going to work with, whether or not those cells grows very well in the type of the bioink material that you're thinking. You have to check the literature, the compatibility of the cell and the hydrogen material that you're thinking. And then you will also see the method of bioprinting that you're using. So if it is extrusion based with air, then you can use relatively less viscous materials as well. But if the system that you have is a screw based system, then you will think like, okay, fine, we can use higher viscous materials as well. Okay. And then you see what fits best. So these are all constraints that you have: the type of the tissue, the type of the cell, the availability of the material, the type of the machine you're using. So all these constraints are there in front of you, and then you make your best decision possible. But what I have discussed now is the technology that are available for bioink design. But for every researcher and what is their application, they can combine either 2 3 of the methods together, okay, or they can use one method individually. Or if the challenge is so unique, then that person has to come up with the another type of bioing design, and like that may not be used by others. Okay, so depending on what constraints you have, you will have to decide which design to use. Got it?
Okay, ma'am, got it.
Okay. So this course is just introduction type of thing, like help you understand what is the technique and what all advances are being made in this field. Things become much more realistic when you start working, and the question that you asked, you will be able to answer better yourself when you start working in this area. Okay. So now we discussed the bioink designs, like what all the bioink types people make and how they design it. Okay. What are the advantages and disadvantages of these designs? Next is forms of extrusion-based 3D bioprinting. Okay, what are the forms that are there, or variants, versions of 3D bioprinting of this type? So we will discuss around 3 types that people have developed. So first type is sacrificial and free-form embedded bioprinting. Okay, so this method was first demonstrated in 2012, so 2011, where a scientist, what he did, he used a fugitive ink. Okay, note the term fugitive ink, Pluronic F127. So beauty of this material is that if you keep this, if you it takes, let's say, 1% of Pluronic, mix in water, okay, and keep in room temperature, then it will gel. All right, it will be in gel state. But if you keep it, the same solution, in fridge, let's say 4 degrees Celsius, then what will happen? It will form solution. So in low temperature, it is a solution, but at high temperature, it is a gel. So it's a very beautiful material. And also you cannot form chemical crosslinks with the material itself. You have to modify it by adding some more groups in it, okay, in order to form chemical crosslinks. So this researcher in 2011 used Prudonic F127 as a fugitive ink and printed it inside a support bath that is now made up of pluronic, modified pluronic, that is called pluronic F127 diacrylate. This is modified, means it has a diacrylate group that allows chemical cross-linking in presence of light. Now, after the printing is done, the entire system was photo cross-linked. Okay, so photo cross-linking allows allowed what? The chemical bond formation in the support bath. After they have done the chemical cross-linking, they just simply washed away the fugitive ink F127. And how did they wash away? They just simply kept the system in 4 degrees Celsius. It became a liquid, okay, and then washed with cold water or something like that. So the ink just washed away. And what you get as a result is some empty channels or empty structure inside in 3D space. Okay, so this technique was a demonstration as a proof of concept for sacrificial freeform embedded bioprinting. Okay, so in this image, you can see this image. There's a nozzle. It goes inside the support bath, okay, and moves in any way. Freeform, why it is called freeform? Because it can move through any plane of Z direction, like anywhere. It can move like this in 3D space. There is no built platform to support the deposition of the nozzle. The 3D space that is created by the support bath, that is supporting the uh, translation of the nozzle and the extruded filament, that is supporting. Okay, so that is why this technique is very well used or exploited to create complex structures like, let's say, blood vessels like this. Okay, and you can create blood vessels of tiny diameter, and you can perfuse them, like add uh like flow media, cell culture media through them. Okay, you can use various version of this technique, like you can embed cells in the support bath. So after the fugitive ink is removed, the cells in support bath will be in contact with a network of channels, right? And then you can perfuse media through the channels, and you can mimic the blood vessel circulatory system in vitro. Or you can also do you can first create the channels, okay, by washing away the fugitive ink, and then seed the cells inside the channel, so you can again create blood vessel structure in vitro. So this is a very powerful technique for doing this type of bioprinting. The support bath property should be kept in mind. What property should it have? First, it should possess very high elastic modulus, G prime. So for the sake of simplicity, let's understand elastic modulus as a measure of how the fluid, how much the fluid acts like a solid. When you talk about solid materials, they are not very easy to deform. Means when you apply some shear force, the structure will remain the same. Like when I push this pen, the structure is pen is right, same it is, right? Unless I give very high bending force, it will not break. If I give very like less pressure, the structure will stay the same. So this is a characteristic of a solid. So the fluids, viscoelastic fluids, when we say has a high elastic modulus, it means it has a very high tendency to act like a solid. Okay. So the support bath should act like a solid. Why? Otherwise, if it is like more like water, if it is more like a liquid, then the fugitive ink as it is deposited inside the bath, it will mix in. It will mix inside the support bath. It will like diffuse out. The filament will not be a straight filament. It will be like some very distorted type of filament. Got it? So in order to support the shape of the filament of the fugitive ink, the support bath should have a solid like property, and also it should have low yield stress. Low yield stress, as we discussed earlier, is the measure of basically the minimum stress that a material can or should be applied, minimum stress that should be applied for it to flow. Here, when we talk about low yield stress, we think in the way that it will help the translation of the nozzle. So if it has, again, very high yield stress, then the nozzle will not be able to move. It will face barrier in movement inside the 3D matrix. So in order to facilitate smooth translation of nozzle inside the 3D space, it should have low yield stress. So these two mechanical characteristics support bath should possess in order to do free from free form means in anywhere in 3D space, in order to do free form 3D printing of the fugitive ink. Okay. Why this technique came into picture? It is because there are various type of biomaterials which are which are having very low viscosity, but in terms of bioactivity, they are very well suited for cell growth. Okay, so you want to create complex structures with soft biomaterials, which in itself is not very good, which itself does not possess very good printability. But how do you print them? Okay, so that is why like this type of variation of extrusion-based 3D bioprinting came in. It came into picture. Here you can deposit biomaterials of low viscosity, which itself if you try to print on a build platform, it will collapse. But if you print inside the support bath with high elastic modulus and low yield stress, the deposited ink will stay in its place. Okay. So I don't know how much you have understood from my description, but if you, I've given a video here that will help you understand how this bioprinting process works. Okay. I don't know if you can hear it or not, but the demonstration does not have any voice in it, so you'll be able to understand. So let me know if you face any issue in seeing the video. So here, what he did, there's a support bath, as I told you. It's quite solid, because as you can see, it's like thick solid. Okay. And inside it, the needle is translating, right? And it created structure like artery channels. Okay. After the printing is done, what they did, they used a water bath which is heated up, okay, in order to dissolve the support bath away. So once they did that, the artery, 3D printed artery structure came out. Got it? This is a demonstration of how free form embedded bioprinting works. Here's sacrificial component. is actually the bath. Or you can also make the ink as a sacrificial component as well. Like both ways work. Got it? Any questions?
Okay, ma'am. Now they will use how it will be developed as an artery.
Yeah. So you can while the printing process, when they were printing it inside the support bath, they didn't load cells here, but you can load cells in the ink that was translating. In the arteries, you can load cells in it, and you have a very complex artery-like structure, and then you can culture it and you can do further study, like how the cells are migrating inside, whether or not they are forming endothelial monolayer or not. Okay, like that. You can do studies like that. Understood? Is there any
Okay,
queries?
okay, ma'am. Okay, ma'am. Got it.
Got it? So here, again, I'm stressing the sacrificial part is what? Is the support bath. Means you are removing the support bath after the printing is over. You can also remove the ink that was getting printed inside. Okay, and cross-link the support bath itself. So you will have a matrix. You will have a matrix, 3D matrix with empty channels, hollow channels. So both ways are possible. That is what I have written here in these 2 points. All right. Uh, the freeform patterns that is obtained by this process, it can selectively be removed from support bath after bioprinting. So what happens when you cross-link the support bath? The hollow channels are remaining. Or what you can do, you can uh, use or you can stabilize the freeform pattern inside the support bath by cross-linking. And after the pattern is cross-linked inside the support bath, you wash away the surrounding support bath by using heat or something like that. So both ways are possible. But the important feature to note is this technique allows construction of complex tissue structures that is not itself possible when you're doing the conventional way, using biomaterials which are like having very low viscosity, and they cannot be printed. Okay, they have a very poor printability when done the conventional way. But using this technique, you are able to print very soft water like hydrogels as well, using a matrix, support matrix. Got it? Any questions? Others understood how this technique works?
Yes, ma'am.
Yes, ma'am.
Okay. This is one variation of extrusion bioprinting. And there is this variation, okay, that is called coaxial bioprinting. Okay. So the first point to note is it uses something called coaxial needle or nozzle. First thing to note. So there is a needle of a bigger diameter first, and inside there is a needle of smaller diameter. So this becomes the shell, this becomes the core, and you can flow two different materials from like through the needle. So from the shell, you can flow one material, and from the core also you can uh, flow another material. So it uses a coaxial needle. Okay, this technique came into picture because sorry, let me reframe. This technique is based on the technique called bed spinning. Okay, researchers have adopted the bed spinning technique here. In bed spinning, what happens usually? Biomaterial like alginate, it is ejected out, okay, from the needle and into a bath. Now this bath a water bath contains divalent cations like calcium ions. And as soon as the alginate threads falls into this bath, it generates fibrous structures. That is the concept that is adopted here from the wet spinning. Usually this technique started with using alginates as a material, but later on people started using other materials as well for this bioprinting technique. So if you want to create fibers, solid fibers, like they do in wet spinning, how will you do it? So as I said, this core and shell configuration are there in these needles. You can flow cross-linker solution that is containing ions like calcium ion from the shell, and through the core you can flow alginate. Okay, and these, they are flowed together simultaneously, they are done. Okay, so the immediate contact of the calcium ion with the alginate will do ionic cross-linking very instantaneously and form a solid fiber. So what you see is that solid fibers are getting deposited on the surface. That is one configuration. Then you can also combine alginate with other materials as well, because alginate by itself um, can be weak when you're talking about culturing those structures for a long period of time. You can mix alginate with gelma, like to do chemical cross-linking after the printing is done. Okay, so this is one configuration. Okay, one configuration of coaxial bioprinting. Now it can be reversed. Second configuration, what you do, you flow crosslinker solution, calcium ion containing crosslinker solution through the core of the needle. All right, and from in the shell you flow alginate. Then what happens? Alginate is now cross-linked in the form of hollow fiber, because the crosslinker is just water, right? Water with calcium, and it will definitely flow out. But there is an issue. If the alginate concentration is not high enough, or if we are since we are instantaneously exposing the calcium ions with the alginate, the strength of the alginate may not be high enough in order to sustain the hollow structure, tubular hollow structure. Is a possibility that when you do layer by layer printing of these hollow fibers, it will collapse. The circular cross section will no longer be circular, because the weight of the upper layers will start deforming the hollow uh, lumen. Okay, so in order to add mechanical stability to these hollow fibers, again we can add some materials. Again we can add some materials in the core itself. So people mix pluronic F127. As I said, pluronic can be easily washed off when you use very cold P-based solution or water bath, because it dissolves in cold temperature. So you can use pluronic mixed with calcium ion. Okay, so that becomes your core solution. And in the shell, you flow your alginate, and that will ensure that when you do layer by layer printing, the core is not empty. In the fiber, the core is not empty. There is a material inside. And once the printing is done, you have like ionically cross-linked and everything. Then you dissolve out the pluronic. Okay. This will give you a 3D structure with hollow spaces inside. These hollow spaces are good, as I already told you, for cell movement, and it will enhance cell viability, overall cell viability of the 3D structure as well. Okay. So here is a demo of how coaxial bioprinting is done. Okay. So first, this is the structure that person has made in the software. Okay. And then they will try to print this using coaxial needles using the bioprinter. Is the structure, all right? You see, the person has to use two print heads. One printhead is containing, let's say, the core material. Another printhead is containing the shell material, and they are uh, like hooked to each other using a coaxial needle. Okay, this is the coaxial needle. There are two inlets, but there is only one outlet, and the outlet is having a configuration, concentric circle configuration. Okay, there is one needle inside the another, and these two needles have different outlets. So the blue material is the shell material, and inside it, the pinkish red color material is the core material. So, any questions here in understanding how does coaxial bioprinting works?
Ma'am, the pink needle is inside the blue needle. That is why
Yes,
it is
yes.
printing like that. Okay.
Yes, that's the configuration, coaxial configuration. There are triaxial configurations as well. So there is one smaller needle inside, then there is another needle outside. Like you can do like this as well. This is needle one, inside one is needle one, then there is needle two, then there is needle three. So triaxial. Then again, each of the needles will have different outlets. So you can uh, make three layered fibers. So there is one material inside, another material outside, another material is outside, three layered, then four layered. Okay. So depending on what you want to achieve, okay. So these configurations are available. But here in this example, there are two needles. One is inside the another, and each of the needle have different outlets. If that person didn't do hollow fibers, but if you want to make hollow fibers, you can just wash off the inner material out, okay, and you will get hollow fibers. Or you can flow some cross-linking solution, as I told you, through the inside of to the core needle, all right, and then also you will get hollow fibers. Okay, understood the concept of coaxial bioprinting?
Yes, ma'am.
Now, you can use multiple materials at a time in bioprinting as well, like in this method. This is called multi-material bioprinting. So different configurations people have adopted. The first one that sounds very easy. is that if your machine has, let's say, 3-4 printheads, and you load different materials like Bioink A, B, C in all the 3 printheads, and you program your G code in such a way that each uh, layer can be printed by a different Bioink. So in here, there is a coordinated movement of the 3 printheads with respect to one another that can be like easily instructed using G code. Okay, but this method takes increases the overall time for the printing. All right, because you have to give every printhead to activate it at different time points, and that's like that is why it is like the most basic one as well, but you can improve it. It has a chance of improvement. Then how will you do multi-material bioprinting if you want to circumvent that issue? Here in this configuration, there are 3 different reservoirs for the biomaterials. Okay, each biomaterial has its own channel, so they are coming into and what do you say converging into a single outlet. So multiple outlets are there that is connected to each of the bioink, and then they are bundled together into a single nozzle. So they're basically mixed at the end stage, like just before depositing on the substrate. But each of these material have their own reservoirs and own outlet channels as well. Okay, so this enables multi-channel, single nozzle, multi-material bioprinting. So there are multiple channels. There are 3 channels, single nozzle. So you don't have to spend, the machine doesn't spend too much time in changing the print heads. Okay, as it is single nozzle, there is one nozzle that is moving in the 3D space. And in this way, you can print multiple material in a short period of time. Then people also use
Um,
microfluidic systems. Yes, yeah.
and why can't we use just one reservoir for all the three material? Why it is so that all the three are required? Because that will be more easier if the application is we are getting only one type of material at last. So why we need these three reservoirs?
That's a good question. So think that all materials cannot be mixed with each other uniformly, right? Let's say Bioink A has a different viscosity. Maybe it's very viscous. Bioink B is like water. So if you try to mix it manually, and there are cells as well. Note there are cells as well. Okay. So let's say reservoir A has Bioink A that is very viscous. B has a less viscous Bioink, and C has the cells. So the step that you said is that mix all the 3 together first. Okay, make a single Bioink and then do the job. There is always a manual error that can happen. Like you will not be able to mix it very homogeneously. And while mixing, note while mixing also, the cells get exposed to shear stress. That can again cause, what do you say, cell death, right? So then the mixing step only you are causing a lot of cell death, and then they're going to get extruded. There also there will be cell death. So a better approach can be you treat each of these components individually. Okay, mix only at this point, at the extrusion point. We are at this point we are not like very much, what do you say, focused on uniform mixing, because cells are just like going to get anywhere between. The high viscous material will be used to, let's say, provide support to the 3D space. The low viscous material may be much more cell-friendly, so cells will have a more tendency to go into the low viscous material, right? And the final structure that you get the 3D structure, you can think that it is holding its shape because of the high viscous material, whereas the bioactivity of the entire structure will be based on the Bioink B, which is low viscous, and cells are in between. And their viability is high now, right? The cell death is lower, so this viability is high. So it can now further, when you try to mature it and all, it will now be able to penetrate into the 3D space further in subsequent days of culture. So that's a one benefit of treating each of these components individually in this type of configuration.
Understood, ma'am.
Now, the third way of doing multi-material bioprinting is using microfluidic chips. So it sounds very fancy, this term microfluidic chip, but it is nothing but uh, what do you say? A, a chip-like structure, rectangular chip-like structure, within which you create micron-size channels. So the common sense says that since it is very tiny, like within the range of micron size, so it will only support laminar flow of the fluid through it. So even if you use very high pressure, all right, you won't be able to see any turbulence in the flow in the of the fluid. That is why microfluidic or micron size channels are preferred to ensure laminar flow, smooth flow of the material. That's it. So within these chips, you can create channels. So, but again, the disadvantage of these chip is that you're working with very small amount of materials. You are using, let's say, 1 ml or even less than those amounts. So if it's a benefit, also if your material is very expensive and very like costly to make and very time consuming to make, and you only have few microliters of material with you, then you can use this configuration and you will get very small structures. All right, but if you are looking to make very big structures using this configuration, then it will take a lot of time and extra money as well. Okay, this configuration is good when you are thinking of making very small materials, like very small structures. So here you can use channels, microfluidic channels. One channel can have one material, another channel can have different material. Okay. And again, they can be combined together to extrude out through a single nozzle. So this is called parallel configuration, like parallelly two material are getting extruded. Then you can use a series configuration where you are extruding segments of first material first and then second material like this. So red material is coming first and then blue and then red, like switching is there, serial extrusion is happening. Or you can, what you can do, you can mix these two channels. Okay, in channel level only you converge it and make one channel, mix it, and then you extrude it. Okay, so these three configurations is possible to make in a microfluidic system that is a very small system. And then you can use this system as a part of your printhead, like how the printhead is going to move and all. Or you can make it as a printhead, like it can be like combined with one of these printheads, or it can be a single printhead, and that can enable the extrusion of the bioink. All right. So these three configurations in its own way is unique, but whatever suits your application and whatever resources and whatever machine type and whatever technology that you have, you can use it and take advantage of that. Understood?
Yes, ma'am.
Hmm?
Mm.
Okay. So there's a demo video that I have for you guys of how they are doing multi-material 3D bioprinting. So in this video, they are using the first type of configuration where simply they are changing the printhead. Okay. One printhead is loaded with Bioink A and another is loaded with another Bioink, and then they are switching. The robotic arm is able to switch between both of these printhead. Okay. So whatever content that I discussed is taken from this review paper. It's a Nature review paper. I have already shared this paper as a reading material in the Google Classroom as well. If you get time, you can have a look at it. Although this paper covers much more things as well. Okay. But for the sake of this course, since this course is very introductory in nature, I didn't cover everything that was there in the paper. I took very small important aspect that I want to discuss with you, and I think is very up to mark and fits well with the intention of this course. So only that much I have discussed in this class. But if you're interested, if you found this technique very much interesting and it is maybe something that you want to work with in future, I urge you to go through this paper completely. You see, the author, Jose Malda, is one of the big shot in this area of extrusion bioprinting. Like he has published very good papers. His research lab is doing very well. So that is why I took this paper, and personally follow their work as well to get inspiration and as well as find solutions to my own problems. So if you are to learn more in depth, maybe not today, maybe a few years down the line, the paper is with is paper is already have supplied in the Google Classroom. Download it, keep it with you. Maybe if you need it, you can go through it later as well. But for the sake of this course, whatever I have discussed in today's class is enough. All right. Next week, we will talk about application of this technique for making skin tissue. Okay. So that paper we will try to discuss in detail. Okay. Like all the materials that they used and how did they characterize that skin tissue is actually formed and all those things we will discuss. So any questions so far? So we have 10 few more minutes, basically 10 minutes to spare, and we can have discussions other than this topic or anything else that you want to discuss. If Let me stop recording so that you will feel more comfortable.